Hey again, everyone. Professor Hartman here. What I want to do this week, as usual, is kind of go through a few problems from that are similar to the homework questions, and also similar to the sorts of questions that you'll be seeing on a quiz or a test or something like that. So last week I just went through two problems from chapter one because chapter one sort of getting you familiar with the principles of physics and stuff. But here in chapter two, we really start getting more into the heavy math, the heavy lifting, you might say. So I want to go through sort of just show you how these things are solved. Right, what we're covering now is called kinematics, and kinematics applies in both one and two dimensions. And in my experience, this may not be true for you, but in my experience teaching physics over many years, it's kinematics that people generally, not everyone, but a lot of people tend to not love kinematics, and it takes a little getting used to. I think the main reason for that is that it's taught early on, and physics is sort of an acquired taste, and it takes some practice. And so, just because it happens early on, that people generally are a little more uncomfortable with it. And so, seeing problems solved, particularly those straight out of the textbook that we're using, I think could be of great benefit. So I have four problems picked out here. Again, these are from chapter two. At the end of the problem section of the text at the end of the chapter. So here, right, what we see is we're told that a rocket rises vertically from rest, and you're given the rocket acceleration until it runs out of fuel at a particular altitude. And then after this point, its acceleration is gravity, and it's downward, right? So this is sort of the important thing to sort of realize. And then we want to know what is the velocity of the rocket when it runs out of fuel. So we want to look at this thing in a couple of phases, I guess, as I would say, right? So for the general picture is like this, right? So we have, like, here's the ground here. This is ground. And, here's our rocket, like sort of like this. I'll just make it like a triangle, right? And it blasts off. And it blasts off with a particular acceleration, right? So the overall acceleration is up, and so it's going to go. It has this positive acceleration a, right? And what that acceleration is doing is it's speeding the rocket up, right? So the rocket starts with zero velocity, and then it's going to be it's going to increase, right? So this is its velocity, let's say. And anytime I do an arrow on top of something, that means it's a vector, right? And the velocity increases, it increases until it runs out of fuel here. Let's say this is where it runs out of fuel, okay? And well, my pictures, I didn't leave myself quite enough room, so let me move over here and do it over here instead. So, okay, here's my ground, right? And then here's my rocket. I'm just going to do, well, I guess I'll do it as I'll draw it out again, right? So there's my little triangle that's supposed to replicate a rocket, and I'll make my fuel exhaust here, red. And okay, so there's an overall positive acceleration, like this, right? That's my acceleration. And what I'm going to be doing here is the rocket is speeding up, right? So the rocket, as I said, right, starts with like no velocity there. Well, just do nothing. And then the velocity increases, it increases, it increases. That's the velocity, right? And let's say at this point here, this is where we run out of fuel. Okay, that's where the things sort of break down a little bit. So, like, what do we do at that point? Well, at that point, the rocket is still moving up, but it begins to slow down because the dominating acceleration is gravity, right? G, and that's a constant, and that's always going to be pointing down. And so what's going to happen is the rocket is going to slow down. Right? It's going to start. These velocity vectors are going to start to shrink. So here, velocity vector, and then it gets smaller and smaller and smaller, like that. And that's my velocity vector. And this is where this is out of fuel here. Out of fuel. Okay, so that's where we're at. So now, let's kind of work through this. So what is the velocity of the rocket when it runs out of fuel? So we basically, we want to know, what is this velocity right here? So this we'll call, I guess we'll break it up into phases, right? That's what I was going to do initially. I'll call this part sort of phase one. Then I'll call this part here phase two. Okay, that's a pretty good way of segmenting it out, I think. So, okay, so for phase one, let's just look at phase one because that's all we're really interested in for part A. Right, so part A, phase 1. Well, so what do we know? I like to sort of go ahead and list our knowns. Right, so our known quantities here. Well, we know we know the acceleration, obviously. A is a positive 3.2 meters per second squared. We know that y, we can say, well, we start at an initial point. Usually the 0 means an initial point. We start at ground, right? So we can call the ground 0 meters. And we can call our final position, y final, if you want to call it that. We can call that 775 meters. Let me make this a little bigger. Give myself some more space here. There we go. Okay, that's 775 meters. And they want to know, okay, so what's the velocity, right? We want v final, right? And we assume that we start from 0, right? We're starting at rest. So we could do this a couple different ways. Probably the best way is to use, we have those 3 kinematic equations, and we don't have time here, so we should use the one equation that's time independent, right? And we can basically, that equation looks like this, that v final is equal to v initial plus some acceleration. Oops, sorry, that's the wrong one. Let's see, I was using the time one. V final squared equals v initial squared plus 2a, and in this case it's y, right? So it's going to be y final minus y initial. And well, we know a bunch of stuff is 0, right? This is 0, because we said that was our initial velocity. And we start at ground, so that's 0. And so we get this expression here, that v final squared is just equal to 2a yf. And we know y final. And we know all these numbers, right? But so I can just take the square root of this actually here. So v final, right, that's going to be the square root of 2a yf. And so that's going to be the square root of 2 times 3.2 meters per second squared times our y final of 775 meters. And that's obviously something that you would want to put into the calculator. So let me do that. 2 times 3.2 times 775, take the square root of that, and we get 70.4 meters per second. So that's the final velocity. And it's a positive number because the velocity is up. All right, we're defined up as positive. So that's the answer to part A. Now, part B. How long does it take to reach this point? Well, once we have that final velocity, this is a much easier problem to deal with, B, because we can just use this equation, that v final equals v initial plus at, right? Again, this is a 0, so we can go ahead and solve for t, right? So t is just going to be v final over the acceleration, because there is no v initial. And now that we have v final, we know that's 70.4 meters per second, right, over our acceleration of 3.2 meters per second squared. So that's going to be, let's see, 70.4 divided by 3.2. It's 22 even. So it takes 22 seconds for this to happen. Okay, so that's parts A and part B. So let's go check out part C. What maximum altitude does the rocket reach? Okay, so now what we're going to do is we're going to look at phase 2, right? And what I'm going to do is I'm actually going to go ahead and erase this stuff just to give myself some more room. So hopefully you've copied that stuff down, or if you haven't, copy it down. Here, just give me a second to erase all this. I guess I could have shifted it over to the right, but whatever. Let's do it this way. Sorry. Erase that, erase that. Okay, so we're looking at phase 2 now. I want to use this picture anyway, so it's part C. Okay, so now looking at phase 2. Basically what we want to say is, okay, well, if we look at phase 2, we know that we're starting with a velocity. So what was our final velocity for phase 1 becomes our initial velocity for phase 2, right? So our initial velocity is 70.4 meters per second, right? Because that's where we ended in phase 1, so we begin in phase 2. Our final velocity for phase 2 is 0 meters per second, right? Because we're coming to rest. That's the whole point. Max height is defined, right? This is what defines max height, right? So anytime you're talking about the maximum height, your velocity is going to be 0. Well, there are some variations on that, but your y velocity is going to be 0. When we start doing projectile motion, you'll see there's some variations there. We'll talk about those when the opportunity comes up. Okay. So here, let's go ahead and do this, right? So, and of course we know that g, before I do anything else, is negative 9.8 meters per second squared. It's negative because it's slowing down. It's a deceleration. The acceleration points down. And so basically we're going to do the same logic as we did before, where v final, right? Well, before I do that, I should just point out one more thing. Our y initial, right, is 775, because now we're starting at the very top. We're starting at the end of phase 1. So what was our final position now becomes our initial position. And so now we can use this equation, right? V final squared equals V initial squared plus 2. Now it's G, right? Y final minus Y initial. My instinct is to use the I for initial, but the book uses that as 0. So I want to be consistent with the book. Final velocity is 0, right, at max height. So what we now have is 0 equals V initial squared plus 2G. And here we can say, Y final minus Y initial. And so let's subtract the V initial squared, right? So I'm going to get 2G Y final minus Y initial equals negative V0 squared. I'm going to now divide both sides by 2G, right? Because remember, I'm looking for Y final. That's my point here, over 2G. And so what that does is that gives me this, right? So it gives me Y final minus Y initial equals negative V0 over 2G. And now I can add the Y initial to both sides. And what I'll get is Y initial minus V initial squared over 2G. And now we'll just plug numbers in. Everything here, so I'll do that here. That's 775 meters, right? Minus 70.4 meters per second, the whole thing squared, over 2 times negative 9.8 meters per second squared. And so let's see what we get here. So it's going to be 775. There's a minus minus, so the whole thing is going to become a plus. So when I do that, I get a grand total, and I add these all things together, I get about 1,028 meters. So the answer, okay. So that is the answer to part C. D, how much total time does it take to reach its max altitude, right? Well, what we can end up doing is just solving for, I'm going to clear this out of the way so I just have more space, and I'll put that back in after when I do my next video. Okay, so how much total time, right? So again, for phase 2, let's find the time for phase 2. And we'll just add that to the time that we've solved for phase 1, and that's our total time. Right, so for that, we can just do this. V final equals V initial plus GT, right? V final is 0, right? So it's 0. V initial plus GT. So therefore, T is negative V initial over G. So negative 70.4 meters per second divided by negative 9.8 meters per second squared. And so let's see what that is, 70.4. That'll be a positive number, as it should be. You shouldn't be getting negative times. So it's about 7.2 seconds. 7.2 seconds. So our total time, T total, right, is 22 seconds, which is phase 1, plus 7.2 seconds, which is phase 2. So that'll give us 29.2 seconds in total. Okay, almost done. Part E, what's the velocity with which it strikes the Earth? And so the velocity with which it strikes the Earth. So now, right, for phase 3, I guess you could call this, right? Phase 3 is we're starting at maximum height, right? So we can sort of think of this a number of different ways. But I would say our max height, right? Since we're starting at max height, now this is for basically the trip down, right? This is the trip down. So we've reached our maximum height. What was our final velocity for phase 2 is now our initial velocity for phase 3. That's 0. Our delta y, let's call it this way, the length, right? So basically the full length that it's going to be dropping, the full height is 1,028 meters, right? Because that's our max height. So we're falling from max height. G is negative 9.8 this whole way down. And so this is basically a free fall problem now, and it looks like this. It's almost as if you're dropping this rocket from rest. Obviously, we're ignoring air resistance. This is 0 because we're starting at max height. And so our final velocity is the square root of 2. G is negative 9.8 meters per second squared. And our delta y is actually negative because we're moving down 1,028 meters. And then make sure you don't have a negative under the square root. That would be a problem. So if we put these numbers in, that's going to be 1,028. I get about 142 meters per second, right? And you get like a plus or a minus when you take a square root, and it's actually a minus now, right? Should be minus 142 meters per second because this is a vector and we're pointing down, right? So that's the idea. Okay, so that is, we'll do this one later. My computer's making kind of a weird sound here, so I am going to, I think, see what's going on with my computer. It feels like it's sort of overheating or something. And I'll add some more videos, a couple more problems. I had 2 or 3 more problems that I wanted to do for this chapter that I think are relevant. But this problem covers a lot of good stuff, so I think there's like some good material in here. So hopefully you found it useful as well. As usual, any questions, feel free to reach out to me.